Okay, Mama Huffman here. We're going to talk about historically what has been our scientific understanding of what goes on in the universe. So we're going to get a perspective on how scientific knowledge has changed and how how the data was collected, and as our methods for collecting them have changed, that brings about new knowledge and different, deeper understandings of what's going on out there. So let's even pause to consider a long time ago, the latest and greatest of scientific knowledge was knowing that the Earth was flat. That was proven true day after day, minute after minute. Just take a look. Obviously, it's flat. Like 3,000 years ago, that was correct science. But okay, along came Aristotle. And Aristotle was the first guy on our list. And he figured out that, you know what? I think the Earth is round because it casts a curved shadow. What I even want you guys to just consider for a second is that Mama Huffman does not know where she put their flashlight. Okay, well, assuming I could find that flashlight. Oh, wait a minute. This has a flashlight, doesn't it? Okay. If I shine the light on the ball and we look at the shadow behind it, I realize it's hard to see back here on the board, but if we look at that shadow, it is round. Now I can turn this spherical object, and no matter how I turn it, it has a curved shadow to it. Now that would be different if it were something that is a circle, not a sphere, but a circle. So like this right here is a circle. Now, at this angle, the shadow would be round, but as soon as I turn it, eventually the shadow would just be a flat line. So that was one thing to consider. And now you also got to think, how can we put a flashlight behind the Earth to see the Earth is round? Ha! The sun. So Aristotle was noticing, this is about 2,800 years ago-ish, Aristotle was noticing that during a lunar eclipse, which is when the shadow of the Earth covers the moon, that Earth's shadow, as seen on the moon, was curved. And so I drew this purple line to extend that out so you can see, oh yeah, that's a curve. And every single lunar eclipse, the shadow was curved. Now, lunar eclipses happen more often than you think. Solar eclipses are the ones that are much more rare. Lunar eclipse happens several times a year. They may happen and you don't even realize it. But anyway, so this was seen frequently enough and okay, round shadow. Now that is only the first piece of data that was figured out as to why Earth is round. We have so much other data. We will discuss that on another day. But anyhow, turned out Aristotle was correct about that, even though not everyone knew about it at the time. Then not too long later came this guy named Aristarchus. Aristarchus came up with the heliocentric model of the universe. Helio referring to the helium, referring to the star, referring to our star, referring to the sun. Helio means sun, centric as in center. And his heliocentric model of the universe, he said that the sun was at the center of the universe. Now, this was breaking news because at that point, everyone knew the Earth was the center of everything. That made sense because you would see the sun move across the sky. You would see the stars if you were tracking them, or the moon move across the sky. Of course, Earth was the center. No. Aristarchus is the first one to figure out that, the Earth is not the center. The sun is the center of the universe. Now, he was wrong about that because the sun is not the center of the universe, y'all. It's the center of our solar system, but he had no idea of a concept of a solar system at the time. So he was wrong about the sun at the center of the universe. But what he was correct about is that the planets revolve around the sun, not revolving around the Earth. So he was the first person to consider that the Earth was not at the center of everything. And that was pretty amazing that he even bothered to think about that. The next guy on our list is a guy named Ptolemy. Now, Ptolemy, it turns out, was wrong about everything that he figured out, but it was still a really important, oh, wow, at the time. What he figured out was some calculations to explain the retrograde motion of planets. Now, retrograde motion, what? Okay, if we track the planets Venus, Mercury, and Mars in the night sky, night after night after night, year after year after year, what you will notice is they're moving across the sky. And then at some point, as you're plotting this data, they go backwards and then start moving forwards again. That backwards movement is the retrograde motion. So as it's going across the night sky, there's a point in time where it goes backwards before it starts going forward again. Ptolemy figured out that this was due to Earth at the center. So he had what we call the Ptolemaic model of the universe. He put Earth back at the center, the sun orbiting around the Earth, and then he said these other planets, to explain their retrograde motion, is that they were doing little mini orbits, little mini shoop-de-doop, like a little mini loop-de-loop in their orbit around Earth. And while they were doing the little loop-de-loop, it would appear to be going backwards during that time. So he was really smart that he could come up with all of these data observations and calculations to prove himself correct. He had the calculations to prove himself correct. Just turned out there's another explanation from this, and he was actually wrong. Here's the actual explanation for what's happening. Notice I said if we track Mercury, Venus, and Mars. Oh, wait, I'm sorry, Mars doesn't do this. My bad. It's only Mercury and Venus. Mercury and Venus do this because they are closer to the sun than we are. What happens, it's like runners on a track. In lane 1 would be Mercury. And as Mercury laps the runner in track 2 and track 3, from the perspective of the runner in track 3, it would seem that they are going backwards. So, and this is just, I guess it's a law of physics. It's just relative motion. As both objects are orbiting, as the inner one, this is the inner one, as it laps the outer one, as seen from the outer planet, we appear to have this backwards retrograded motion. The planets are not actually orbiting backwards. That's just our perspective. So anyway, but Ptolemy, meanwhile, he calculated that to prove himself as saying the Earth is at the center. He was very popular at the time because people wanted to hear the Earth was the center of the things, of everything, okay? But anyway, just turns out he was wrong. Now, thousands of years later, well, 1,500 years later, we get to Copernicus. Copernicus agreed with Aristarchus. Copernicus was very unpopular, particularly with the Roman Catholic Church at the time, okay? Because this is going against church teachings. But Aristarchus Copernicus agreed with Aristarchus that the planets revolve around the sun, that the Earth is not the center of everything. Copernicus is the first person to come up with the idea of a solar system, and that the sun is the center of our solar system, and that's it. It's not the center of the universe, but that there is this thing called a solar system, because before Copernicus, we just thought it was just one universe and one thing. It's all one thing. Well, no, we got this idea of a solar system, a star, the sun, with planets orbiting around it. Okay, so, and he was correct about that a solar system is a thing. All right, not too long later comes Brahe. Brahe was crazy, quite frankly. He's like a Kardashian of his time, would have very much been in the tabloids if there were tabloids in the 1500s. But anyway, he developed a space observatory. He built this physical space for people to come and study space. And he made very precise observations about things without the use of a telescope. He used what was called an astrolabe. Let me see if I can get you an image of the astrolabe, but it was, it's like an entire part of the building. Let me see, astrolabe Brahe. His was a very big one. Okay, yeah. Here's like a artist drawing of it. See, this astrolabe is the swoop through the middle of the screen. So it's like this entire, it's not just something you hold in your hand. It was this entire part of the building. And so then they would look at the night sky and track the positions. Like, here's this astrolabe that stays in place. Well, here's Mars right now, then here's Mars, then here. So we could very accurately track the positions of things in the night sky. So that increased our ability to collect data about the universe. Now, here's where he was a little bit, he thought he was seeing advanced civilization on Mars. He thought he could see sewer systems and stuff. No telescopes, guys. No telescopes. So he was a little bit crazy. He ended up dying when like someone poisoned him. I mean, like I said, he would have been in the tabloids. Okay, then there's Kepler. Kepler, you've heard his name before. He's got these Kepler laws of motion, laws of planetary motion. He did that thing about like the redshift and calculated that. He was very popular in his day. He was also a very good-looking guy, very charismatic. People liked Kepler. Anyway, his first law of motion, first law of planetary motion, we have mentioned briefly before, but that's just saying that planets have an elliptical orbit. He's got a calculation for this. Anyway, but that it is an oval with two foci rather than a circle with one focus. So that means that the planet is not the same distance from the sun all year round. Okay. His second law of motion is that planets move faster when they are closer to the sun. Now, this is the same thing as a figure skater effect. Imagine a figure skater on the ice and he has their arms spread out and they're rotating on their skate, but then pull their arms in and they start to whip around real fast. Okay, when we're in class together, we can do this. I've got a sit and spin. We can see this happening with rotational objects. As you lower that axis of rotation, the object will be spinning faster. Okay, so anyway, this applies to planets in the sense that a planet such as Mercury that is closer to the sun is orbiting faster. Now also, furthermore, if we pull this back up to the planets with an elliptical orbit, the point in time that the planet is closer to the sun, it is moving faster. Here's the part that's going to be a bit, what? On Earth. Earth moves fastest in its orbit in December and January. Think about that for a minute. It is fastest in December and January because it is closest in December and January. But Mama Huffman, it's cold. Yep. But that's because of our axis. Now, this is not one of Kepler's laws, but here, this just points this out. Here's the sun, the source of our heat. In December, the planet is closer, but the northern hemisphere is pointed away. So the northern hemisphere is in winter. Australia is in summer in December and January. Okay. Then in June, July, we're in summer because our axis is pointed towards the sun, but the planet itself is actually farther away. Now, this is not drawn to scale, but nonetheless, just to give you an idea of what I'm saying. Okay, Newton's third law. We have also mentioned this one a little bit before too, but the time it takes for a planet to orbit depends on the distance it is from the sun. The closer it is to the sun, the less time it takes to go a full orbit around. So it doesn't take Mercury that long to move around. The farther planets like Neptune is a lot farther. It takes a lot longer to get around the sun. Duh. Some examples, Neptune is about 30 astronomical units away, 30 times the distance between Earth and the sun. That far out there. It takes Neptune 165 Earth years to orbit once around its sun. So no human will ever be alive for a full Neptunian year. It's too long. Okay, two more dead white guys to talk about. Galileo, he invented the telescope. And I'm pointing this out to you because I want you to realize, all of these other guys did what they did without a telescope. Yep. Now, there were telescopes at the end of Kepler's life. Kepler and Galileo were alive on Earth at the same time. So there would have been a little bit of overlap there. But anyway, Galileo was the first to find moons orbiting Jupiter. Now, that is great because, wow, okay, there are other things that have moons. But here's the significance of that. If there are these moons orbiting Jupiter, as in very clearly, obviously, definitely, without a doubt, those moons are not orbiting Earth. There's no argument for that. Those moons are not orbiting Earth. That was just furthermore, oh, yeah, okay, the Earth really isn't the center of the universe. It's not. It's not even the center of this solar system, let alone the center of the universe. So that just kind of helped with that. And then it was also really cool. Galileo, by the way, if I'm remembering correctly, he's the one that went blind before he died because of staring at the sun through his telescopes. Yeah, so don't stare at the sun. He also found sunspots on the sun. We can talk about sunspots in class sometime if you want to ask me about that. Okay, the last dead white guy to talk about is Newton. Isaac Newton. We know him for his laws of motion, also for gravity. Here's why gravity is important in space. Okay, yeah, gravity, the apple falls. Okay, great. But what does this have to do with outer space? All the while, up until Newton came around, people, scientists, religious leaders, the general public, were all still very much struggling with the idea that the planet is orbiting the sun, or quite frankly, that anything orbits anything else at all, because why would it orbit? Why does that happen? Gravity explains it. Here's the deal. We know about inertia, Newton's first law of motion. An object at rest will remain at rest. An object in motion will remain at motion at the same speed and direction. Those things are true unless they're acted upon by an outside force. Okay. Orbital motion is circular motion, rotational motion. That is a constant change in direction. Guys, if I spin in a circle here in my chair, I am constantly changing direction. Now, the way I can do that is because I keep pushing on my desk. Okay, so I keep adding another force to keep me rotating. What adds a force to these planets to keep them rotating? Gravity. Gravity is the force. So here's what I'm getting at in this little diagram here. The big blue thing is the star. The little grayish green booger looking color is the planet. The planet would keep just going forward. Okay, it has its forward inertia. But the gravity is pulling it into the sun. But wait a minute, then why doesn't the planet just crash into the sun? Because that forward inertia. Okay, so those two things balance each other. And the resulting motion is this circular orbit, the rotational motion around. Problem solved, book closed, Earth orbits the sun, mic drop. Okay. So this was so important at the time because it helped the public and other astronomers in general to accept that Earth actually orbits the sun and that planetary orbits could exist in the universe. All right, and thus ends our talk about dead white guys. There's so much more to talk about, guys. You know what? Let me just pause here to say, go watch, what is Hidden Figures. Watch the movie Hidden Figures, okay? It is not only white guys, it's not only white people, it's not only dudes that have done important stuff, but they're the ones that get printed in our textbooks. Ugh. Anyway, all right. So there's some historical perspective. And stop.